Excellent. So welcome back to a fourth lecture. For those of you who were looking forward to some problems, that's not what you're going to get today. So what I'm going to tell you today is about more about polar codes. We just started describing what they were last time. And today I'll very quickly review what we did last time and start jumping into the complete definition and the analysis of polar codes. I will give you a fair amount of the details, and whatever is missing, you'll be able to find papers that will cover it. Okay. All right. So recall that we defined this notion of a binary symmetric channel, which flips bits with probability p and keeps them probability 1 minus p. We defined the capacity of a channel, and we told you that the capacity of the binary symmetric channel with parameter p is 1 minus the binary entropy of p, where the binary entropy of p is defined as follows. All logarithms are to base 2. And what we really want to do is to say, well, suppose I fix some delta, which is, positive constant, and I want to operate at a rate which is a little less than the capacity. So the rate is c minus delta, or delta is c minus r. Question that we are asking is, how efficiently can we build coding and decoding as a function of this delta? And we want to get to algorithms which will be able to run in time polynomial in 1 over delta and correct some fraction of errors with high probability. Okay, so we told you that Arikan invented these polar codes, and then Guruswamy and Shia and Hassani Ali Shahi and Nirbanke gave the analysis, which tells us that yes, these codes actually achieve this phenomenon. Okay, so those are the codes that we want to define. And again, another quick reminder, what we told you last time was that instead of building an error correcting code, it suffices for us to build a matrix which can be used for compression. Its compression will map a sequence z to the vector m times z, and the decompression will take m times z and produce as output z, hopefully with high probability when z's are Bernoulli and independent and identical random variables. So this is what we want to design, and if we can design it, then we are done. This was the analysis, and I will not go over the analysis again. I didn't go over it last time either, and we'll do that again today. So in order to build this matrix M, what we told you was it suffices to build an invertible matrix called P, and which has the following property, that when I look at the top part of P as M, call it M, the bottom part and call it R, then entropy of RZ conditioned on MZ is very close to 0. This is what we want to build. But we will build this by building the square matrix slowly and iteratively. And the slow construction will have the feature that slowly, as you look at various coordinates of p times z sub I, if you look at different coordinates of p times z sub I for different I, some of them will be very, very random, and others will be very determined given the other quantities. And this is the polarization that we want to achieve. We'll do it by a sequence of simple steps, each one of which will be doing a little bit of differentiation between identical random variables. What's the base of this process? Well, we could start with many other processes, but this is the one that we will work with. Given two bits u and v, these are two elements of GF2. We output u plus v, which is the XOR, because we're doing all operations in GF2. So the sum mod 2 of u and v. And what we noticed was that u plus v is more random than either u or v. Hence, v conditioned on u plus v is less random than either u or either v. Okay. So when we managed to create two identical bits, let's say u and v, and now differentiate their entropy a little bit. One is slightly more entropic and the other is less. And if we keep repeating this process, we hope that we can get very, very, very entropic bits somewhere and completely non-entropic bits conditioned on those somewhere else. What does it mean to actually repeat? This is what I want to get to. So this is why I switched to slides, because I have these pictures and it's very neat. I'll just change my notation because with U and V, I'll soon run out of the alphabet. Now A and B, I have lots of alphabet to go. A and B are 2 bits. And what we just said was described by this Z operator. You take these 2 bits and you add them. That gives you A plus B. And then B is also reported as it is. This is the first step of the process. If I want to repeat it, what do I mean? First, I'll double the number of bits available, A and B, C and D. Apply what I was planning to apply to A and B independently also to C and D. So I have C plus D and D. But this is just repeating the process on 2 independent sets, and they have not been correlated yet. Next, what we will do is to correlate the 2. And to correlate the 2, let me redraw the thing. So these green arrows are just moving the bits around. They're not doing any operation. A plus B and C plus D are both identical types of bits. And furthermore, they're independent of each other, right? Because this comes from the top half, that comes from the bottom half. The top half has nothing to do with the bottom half. So let's take those 2 and apply the Z operation again to those 2. These are independent Bernoulli identical bits. When I add the 2 of them, I'll get something which is more entropic, and then the remaining guy will be less entropic condition on that. So notice that at least if you keep following the upper path, if you keep repeating this kind of a process and keep repeating the upper path, this top bit is going to be very, very, very entropic, eventually almost 1/2 biased. Okay, that's the most a bit can be. Its entropy can be at most 1, we'll get a 1. The bottommost bit is certainly going to go to become almost 0 entropy, because each time its entropy is reducing. What about what happens in the middle? Well, we don't know, but let's go ahead and repeat the process. So at least one more step of repetition. So I took this picture and copied it here, with the only difference is that these are now called EFGH. These are new collection of independent Bernoulli bits. Having done that, I got 8 bits, these ones. Once again, I say, notice that the first bit here looks the same as the first bit there. The second looks the same as the second. The third looks the same as the third, etc. So for instance, if I look at the third bits here and here, I move them here and now do the Z operation on them. Okay, so each time I'm taking 2 identical independent bits. These are identical independent, even condition on everything above. And then I say, oh, this is more entropic than that, and this is less entropic, the condition on that. Okay, so this is the process that we are applying. Is the process clear? If we repeat this process p times, then we would have needed to start with 2 to the t bits. We will end up with 2 to the t bits. Each bit here is a parity of some subset of these bits. So this whole thing is represented by some big 2 to the t by 2 to the t matrix. And one of these matrices is the one that will do for us. Now, which part of this matrix will be called M and which part is going to be called R? That is a non-trivial thing. We will just claim it exists. But even proving that it exists is non-trivial. And that part we might give you some hint about. How do you prove that there is some way of reordering these output bits so that some part is very entropic and the other is not? Okay. Rania resembles the Walsh-Hadamard transform a lot. Yeah, Walsh-Hadamard does something very similar. And yet somehow something is very different. Okay, so I am not seeing all linear functions of the bits over here, but instead some carefully chosen collection of bits. And each one of these bits is a parity of exactly 2 to the I of these bits for some integer I. So Arikan, what he did was he defined these things, and then he said, well, these are actually, there's some underlying notion called martingale. So in case you haven't seen this notion of a martingale, it's just a sequence of random variables, x0 to xt and so on, which has the feature that when I look at some marting value expectation of xt, condition on all the past, x0, x1, so on up to xt minus 1, this is exactly xt minus 1. Okay, so that's what a definition, what calls these things a martingale. And Arikan noticed that, look, he was creating these matrices of size 2 to the t, n equal to 2 to the t for all choices of integers t. And associated with this creation process, he associated one long, infinitely long sequence of variables whose value is between 0 and 1, always between a real number between 0 and 1. And these would be martingales. And he proved that these martingales actually polarize. So look, I mean, I have some variable xt. What is the expected value of xt? Well, it's equal to xt minus 1. Or what's the expected value of xt minus 1? It's xt minus 2, and so on. So at the end, this is a random variable with expected value equal to x0. And you can assume x0 is some fixed constant when you're starting. Okay. So at the end, this is going to be a random variable whose expectation is known, but it's also between 0 and 1. What is it going to look like? One extreme, well, xt may be equal to x0 with probability 1, or it could be some continuous distribution between 0 and 1. One extreme is it roughly looks like 0 with probability 1 minus x0 and 1 with probability x0. Okay, and that's what we call polarization. This real numbered random variable which sits between 0 and 1 eventually converges to being either almost 0 or almost 1. This is what we call polarization, and this is what we will prove. And if we can prove polarization of the following type, that the probability that this random variable is between some, very close to 0 or very, very close to 1. Think of tau, delta, and epsilon as all being almost 0, actually 0. If xt, the probability that it is not somewhere close to the extremes is extremely small, then the code that we will build will be that close to capacity. So epsilon plus delta, these two quantities add up. And we will be able to decode it efficiently, actually, with probability n. N is the number of coordinates times tau. So this parameter, so notice when you look at a random variable and you say, oh, how close to 0 is it? How close to 1 is it? And what's the probability with which it's neither? One would think there'll be some symmetry about the two sides, but there is not. This plays a very different role because of the kind of martingale we are creating. This is symmetric to that because these two are going to add up. Whereas this is very special. We really want to create martingales, which in 2 t steps will satisfy the property that n times tau is much less than 1. It's almost 0. So almost we want tau to be doubly exponentially small in t, because n is exponentially small in t. At least it should be more than, smaller than 1 and 2 to the t. It should be like 1 and 4 to the t, 10 to the t, 100 to the t, etc. This behavior is what we will try to analyze for a particular martingale. In the rest of the talk, what I'll try to explain to you is, where does this theorem come from? How does this matrix, this very neat Z transforms and iterated in the butterfly, lead to this kind of a question? And how do you prove theorems like this once you have martingales in hand? Okay, and when you put the two together, you get this wonderful result of Arikan plus Guruswamy et al. And Hassani et al. All right, so what is our martingale going to be? What we're going to do is pick, so we fixed some t. That means we've created this thing which we started off with 2 to the t vectors here and 2 to the t bits there, and end with 2 to the t bits. We'll pick a random row over here. Okay, and look at this entry here and ask, what, this is a random variable, it's 0, 1 value. What is its entropy conditioned on everybody above it? Very, very significant that we're looking at above and below. I cannot invert this picture because of the way the Z's are drawn. Things up there have high entropy, things low have low entropy, and we are trying to look at this specific thing. So that's all we'll look at. What is the entropy of this bit conditioned on the things above? Polarization says, For most of these things, this entropy is either 0 or 1. So let's pretend it's either 0 or 1. Not very close to with high probability. Let's ignore all that. Let's pretend it's just actually 0 or 1 and so on. Well, when it is 1, what it says is that you can tell me all these bits. This guy is completely random because that's the entropy of this bit. So when I'm compressing, I should not ignore this bit. I should tell you what it is. So this should be part of the M part of my matrix. Okay. On the other hand, if this entropy of the same bit is 0 condition on the things above, then I can safely skip this bit. If you manage to guess the first so many bits, first I bits here, then you can also guess the next bit here. Okay. So this bit either has entropy 0 or 1 condition on all the things above. If it is 0, I do not need to, this is where I'm gaining in my compression. I don't tell you what the value of this bit is, so that's one less bit I'm telling you. And if it is 1, I will tell you what the bit is. Now, how many of these bits are going to be highly entropic and how many of them are going to be lowly entropic? Well, that's not up to us. It's completely determined by the entropy that we start with, right? Because when you add all these entropies of this bit condition on the things above, plus this bit condition on the things above, plus this bit condition on the things above, well, you get the entropy of this entire vector. And the entropy of this entire vector is the entropy of the entire vector there. The entropy of this vector is n times entropy of one of these variables, entropy of P. So the entropy here is n times h of P. The entropy there will have to be n times entropy of h of P also. Invertible transforms do not change the entropy. But which of these and how many of these entropies can be 1 then conditioned on the things above? Well, each time I'm adding 1, I can only add it exactly n times entropy of time, P times. So this tells us that once we have polarization, perfect polarization, we have compression. If it is imperfect, then you lose a little bit, like here and here and here and there and so on. Then all of these work out. Okay. So we won't worry about those little epsilons and deltas for the moment, but that's what we are shooting for. Okay. Questions at this stage? Feel free to unmute yourselves and ask if you feel like. Okay. All right. So that's the iterations. Now I want to tell you how can you encode and decode in this thing. Encoding should be obvious, but it sort of it sets up the recursive framework, which is what we're going to use in the decoding as well. It's really simple, right? I mean, I'm going to redraw the butterfly slightly. Initially, I had said, well, I'll take things in pairs here and pairs here and pairs here. Instead, my pairs are now going to be drawn this way. But that doesn't change the picture. It doesn't change anything except I've reordered the input bits. And they were just independent, identical bits anyway, too, so it doesn't matter. So I take n bits that I want to start with, divided into the top half and the bottom half. Now do a coordinate-wise XOR of the top half with the bottom half. That gives me these bits. And then leave the bottom half as it is. That gives me those bits. Now, polarization simply says, now recursively apply polarization to the top half and recursively apply polarization to the bottom half. At some point, you're left with one bit in each one of these entries. That's that stage you're done. Okay. So as long as you have more than one thing, you'll have 2 to the power of some number of things, divide into exactly 2, take the top half, take the bottom half, combine it according to this process, and then repeat. Okay. That's the encoding process. It's fairly clear that this is a n log n time encoding process. The only thing that we don't tell you is, okay, which of these bits are highly entropic and which ones are not. But it's some calculation. We have to do it. We do it before any of the compression is actually happening. We are going to analyze this matrix offline, figure out which subset of bits need to be announced, and then as soon as Z arrives, we will output those bits. Another Z arrives, we'll output the same set of bits. Each time, it's always the same set of bits, right? Good. Isn't decoding identical to encoding in reverse order? Great question. So let's actually look at decoding. First, notice what is decoding? Well, decoding will, best way to think of it is actually some of these bits are not going to be given to me. They're going to be erased. Okay. And we are going to say, ask the question, how can you invert this map? Right? We are not going to get all of these bits. So decoding has a challenge. We've compressed it. And once we've compressed it, we don't know how to figure out this bit. We could do exponential time calculations to say what is the entropy of this bit condition on all the things above, but that's exponential time a priori. So we need to do that effectively, and I'll be effectively telling you how to do that calculation also. But still, we can look at the top half here. And what do we know about the top half? These are a collection of identical Bernoulli bits, which are all independent. The probability that any one of these bits is 1, the Bernoulli parameter, depends on the probability with which these bits are 1. But it can be something they can easily calculate. It's if this is 1 with probability p, this is 1 with probability like 2p minus p squared or something like that. Okay. So we can calculate the probability with which each one of these bits is 1. And now notice I have its compression sitting here according to the polar coding process. I should be able to decompress and figure out all of these bits. Okay, all of these bits. And maybe we can do the same thing in the bottom, and now we are done. Okay, this is clearly not going to work. Why? Because, of course, the top bit is going to be, given to us. The next bit is going to be likely given to us, etc., etc. But as we go down, there are more and more question marks. For all we know, the bottom half is just all question marks. Okay. If it's all question marks, how are we going to recover from here to this part? We can't do that. What we can and should do is, well, notice that actually, I'm not trying to compute these blind. I'm going to have to use the information about the things above. Now, that's where we are told that the entropy is small. Okay. So maybe I should use this information, which is the same as knowing this information, right? It's invertible. Maybe I should use this information in determining something here. What thing? Well, the thing we can look at is we can look at one of these bits. So let's call this u. Let's call the corresponding bit here v. I've told you what u plus v is, maybe the top half has decoded completely successfully. Now, at the very least, I should know what is the probability with which this bit is supposed to be 0 or 1. Before I even look at any of this information here, I should ask the question, what's the probability with which this bit is supposed to be 0 or 1? Well, I can calculate this probability. It's, if I give you 2 bits and I say the parity of these 2 bits is something, you can back calculate what's the probability with which one of the bits is 0 or 1. Okay, in fact, it's very, very simple because these are identical independent bits. If the parity is 1, then, with 50% probability, u is 0, v is 1, and with 50% probability, v is 0 and u is 1. Okay, so it's 50-50. If, on the other hand, the parity is 0, then we know more. So we do know how to calculate this probability. Unfortunately, the probability with which this bit is 1 may not be the same as the probability with which that bit is 1. It's not the same as the probability with which this bit is 1. So these are all different. So we started off, we had identical Bernoulli bits and identical and independent Bernoulli bits, and we were trying to decompress them. Now we are left with the problem now of non-identical, but still independent Bernoulli bits. So how can we try to recover non-identical independent Bernoulli bits? Well, very simple. You do in math what you usually do when your induction fails. You strengthen your inductive hypothesis. So our inductive hypothesis is no longer going to say, I can recover independent identical Bernoulli bits. It will say, I'll recover independent non-identical Bernoulli bits. I should be told for each one what is the probability. Z1 is 1 with probability P1, Z2 is 1 with probability P2, P3, etc., up to P sub n. If you tell me all that, I will calculate Q1, Q2, and so on to Q sub n over 2. What's the probability with which these bits are supposed to be 1? Apply the recursive process, figure out all of these bits. Condition on that, I'll ask the question, oh, what's the probability with which this is 1, R1, R2, and so on, R sub n over 2. Okay, I have this, and now recover. Okay, this works out perfectly. The only thing that I have not told you is what happens at the end. I'm here, what should I do? Well, there are two cases. Well, the value here happens to be 0. Well, nothing to do. If I have a 0, then I report a 0. If I have a 1, I report a 1. If this value is a question mark, then I know what's the probability with which this bit is supposed to be 0. Right? That's what I've been calculating all this time. So that's the input to the problem. It tells me what's the probability with which this bit is 0. I have this probability with which this bit is 0. If that probability is greater than half, I output 1. If it's less than half, I output 0. So that completely specifies the decoding algorithm. It's clear that it's also going to be an n log n time algorithm. And if you inductively make, stating this properly inductively, that at each time when I look at one of these bits, I have correctly calculated its probability conditioned on the things above. If you make that assertion precise and formal, then everything follows, and it will follow that, oh, at the end, the probability with which this guy is being incorrectly predicted is really related to the entropy, and the entropy of all the bits conditioned on the things above. All the omitted bits conditioned on the things above was negligibly small, so we will never make a mistake. With high probability, we will not make a mistake. Okay, so that's how you prove this statement, that when you apply the decoding, you get your correct answer with very high probability. Okay, so what I have told you is how to encode, how to decode, and of course what the code is. Okay, almost everything except that we didn't tell you which of these bits you should suppress and which ones you should publish, but that's one non-uniform computation for every n. It's not a function of the bits that you're compressing, z's. It's just a function of the original problem description. Okay, so the decoding is done. Questions at this stage? Which subset of the bits that we're going to output does depend on P. The number of bits that we would want to output should depend on P. But notice that we are only going to do this for the parameter P. There we don't have to say P1 to Pn. We don't have to take those into account. The P1 to Pn is needed once you've been told which subset of the bits are going to be output. Okay, then when the actual bits come in hand, then we start looking at this thing carefully and we say, oh, what should we do? How should we recover the z's? At that stage, you will have P1 to Pn. So you will need to know n and p to figure out which subset of the bits are to be output and which ones are not. And it makes sense. I mean, if p is 1/2, we would output all the bits. If p is 0, we would output none of the bits. And in between, we will go from many to few, but it's not the first 10. It's not the first so many. If that was the case, I would have told you. It's this one, and then this one, and maybe skip this, and then this one, and then maybe skip, and then this one, and skip. Okay, things like that. All right. So now comes this thing. So how do you analyze this martingale? So recall what we're going to, the neat thing about this martingale that we're going to look at is the following. So really what I'm going to do is, there's this polarization butterfly. This butterfly, what does it look like? At each, there are t+1 columns. And in each column, you have 2 to the t bits written down. Okay, so it's really looking like a matrix. It's not just a layered graph. It's really, there is a notion of a row over here. Okay. So we are going to pick one random row and ask the question, what's the entropy of any one of these bits conditioned on the things above, this bit conditioned on the things above, this bit conditioned on the things above, etc. I will define variables z0, z1, z2, and so on up to z sub t. Or sorry, I'm going to look at entropy of this row condition on the things above. So I will be looking at x0, x1, x2, and so on up to x sub t. And the claim is that this sequence is a martingale. Martingale is a function of what? There's only one random variable at this stage. That's this uniform random choice of I. The others are really distributions. They're not random variables. There's one random variable called I. Pick a random row. Once you have this random row, we are going to claim that actually, as I go along, the entropy of this guy condition on the things above. Well, this I can write down. The entropy of this condition on all the things above is exactly entropy of P. This bit was independent of all the others, and it's Bernoulli with parameter P. This guy is one entropy of P. All of these bits have entropy, with probability 1, x0 is entropy of P. Okay. As we go along, some of these bits have, some of these bits have lots of entropy condition on the things above. Other bits might have very little entropy condition on the things above. Okay. But when you add up all the entropies at a given level, what will you get? You get the entropy of the whole column. The entropy of the whole column is going to be exactly the entropy of that column, because each one of these steps is an invertible map. Okay. But that doesn't prove that this is a martingale. To prove that it's a martingale, what I need to say is, suppose I know that, look, I've reached this vertex, so one step before the end, I have reached here. And I know what its entropy is of this guy condition on the things above. What does the entropy of this guy condition on the things above look like? This is what I need to know. Well, how do I get the next bit? Well, I'm going to pick another. So in this picture, what it's going to look like is I'm going to pick another bit over here and look at its entropy condition on all the things above. Well, it turns out all the odd bits over here and the even bits are, coming from very different processes. So these two are actually identical and independent. That's the way we chose them. Okay. Anytime I apply a z, the two variables are identical and independent. After I apply the z, the combined entropy is the same. One of them is higher and the other is lower. So after any one of these z operations, the average entropy is preserved. So the expectation is preserved. This is a martingale. Okay. So that's what we've got. What we need to say is actually most of these values at the end are going to be very close to 0 or very close to 1. There's a tiny probability that we'll escape and be in the middle. This is what we need to understand and analyze. So in the rest of the talk, I'm going to give you, the rest of the talk is all about martingales and try to say, how do you analyze and state statements like this? I'll give you a little bit of intuition into what this question really looks like by giving you a few example martingales, which are simpler than the actual martingale that we want to analyze. The martingale we want to analyze is this one, but we can create martingales of our own to give some idea, and then I'll state a couple of theorems, and that'll be the end of the thing. So recall, we are interested in a sequence of martingales, a sequence of random variables which are bounded between 0 and 1. Okay. This is not the usual thing that, at least in computer science, we've seen. Computer science, studies lots of martingales, but these are typically unbounded things. Okay, so these are random variables that are going to take any real number as a value, and you try to prove that after n steps, you're very close to, square root of n or something like that, or you do some scaling and which doesn't affect the expectation, and then you try to prove that you're very close to the expected value. So get Gaussian concentration. Today, what we are trying to say is not that these variables are going to concentrate and with high probability be roughly what their expected value is, but rather they're going to polarize. With high probability, they'll be the maximum. With very high probability, they'll either have the maximum value or the minimum value. And the probability of being one or the other is dependent on what the initial value is, so that the expectations are preserved. Okay. So that's the kind of a process we want to study. So we want to say that the limit of this thing is a Bernoulli random variable. Okay. So here are some example martingales, all created to be simple, just to give you a little bit of a sense. Let's look at two example cases here. Okay. Suppose I take a martingale. For each time step t, I define what happens to it in one step. Xt plus 1 is xt plus 2 to the minus t with probability 1/2, or 2 to the minus t with probability 1/2. Okay. At each time step, you either add a little bit or you subtract a little bit. How much? 2 to the minus t. And the probabilities by which you add and subtract are set up so that the expectation of xt is exactly the expectation of xt plus 1 is xt. Okay. So this is a martingale. This is a good example of a martingale. What happens when you run this process for t all the way going to infinity? Well, initially you are, say, here. After one step, you're either here or here. After one more step, you're here, 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 here. And pretty soon, by the end, you're more or less, approximated by the uniform distribution on the interval 0 to 1. This is an example of a martingale that does not polarize. Okay, this is the kind of phenomenon we want to say does not happen with the Arikan martingale. Here is another process. At any point of time, xt plus 1 is the square of xt with probability 1/2. So notice that we are talking of real numbers between 0 and 1. The square is a real number between 0 and 1. But if you're close to 0, you're much closer to 0 after one step. If you're close to 1, you're also much closer to 1 after one step. Sorry, that's not the part that's closer to 1. You're further away from 1, but this guy is symmetrically closer to 1 after one step. And the two options are chosen so that when you take the average, you get xt. Okay, so in expectation, xt plus 1 is xt. But if you're close to 0, you're very, very close to 0 in one step. This turns out polarizes really strongly. This is the kind of polarization that we want to see with the Arikan martingale. So we really want to prove that our martingale does not behave like this. It behaves like this. In fact, none of the above would have been good. Okay, we really want it to be this kind of a thing. Okay, so how do we manage to prove something like this? Well, you can study the Arikan martingale, and my student drew some plots which are kind of faded here, but you can sort of see if you started off and you ask, this is the shades over here are telling us how many, how dense is this path, how likely is this path. So some of these paths lines are looking solid because there are lots of little faded red lines like this that have joined over there. Okay, they're very close to each other. So you see that actually it is, with high probability, you started off here and you applied the Arikan martingale. With high probability, you're heading here or there. And the probability that you're somewhere in the middle is very low. But can we prove this analytically, and how do you do it? So we looked at it. It was very challenging, but the information theorists had been making lots of advances in being able to analyze it. And what we realize is the following, and it's a nice probability insight. What we really know about the martingale is how does it behave in one step, right? After one step, what happens to it? Initially, these two are identical, equal. These two are going to be the entropy of those two, and this is conditional entropy, etc., etc. So I could probably tell you what happens in one step. If you ask the question, what happens in t steps, and tell me that after t steps, the probability that you are close to 0 or close to 1 is exponentially, not close to 0 or not close to 1 is exponentially small in t, where closeness is defined maybe doubly exponentially close to t to 1 or close to t. I don't know how to prove those kinds of statements, at least not right now, because when I look at this martingale, there's a lot of complexity, but the most I'm able to do is look at one step here. So what we realized is what we need is a tool which can tell us what happens, how can we relate what happens in one step to what happens in many steps. And these are sort of formal statements about what we want to happen after many steps. The probability that you are between these two boundaries is extremely small, even etc. etc. Okay, so when you pick this tau to be much smaller than exponential in t, the probability that you're not in this that close to the boundaries is still exponentially small in t. That's what we want to prove. On the other hand, what we see is what happens after one step. And what do we see after one step? Well, let's look at let's look at some of the bad examples. This bad example here, this one doesn't polarize. And the reason you can explain that lack of polarization is after some time, this martingale is not moving much. Okay. After time t, the maximum distance it will ever move by in the future is 2 to the minus t, or 2 to the twice 2 to the minus t, or something like that. And in fact, in one step, it's not moving much. It is not really showing a fixed positive variance. You can say that, look, a martingale sits between 0 and 1. If it is close to 0, it should not move much. If it's close to 1, it should not move much. But if it's somewhere in the middle, you expect it to move quite a bit, right, in one step. Well, this is not showing that kind of movement. Even if you're close to half, after t steps, it's only going to move by a little bit. And that is what kills this kind of an example. And we say, well, okay, if you want to not have that, then you should have some requirement saying when the variable is not too close to the sides, it moves enough. There's positive variance if you're not too close to the sides. And the quantification tells you exactly what we mean, but we mean it in the weakest possible way. Okay. If you're not at the extremes, then you move. Okay, move at least a little bit. Whoops. This is a condition we call variance in the middle. It's just a qualitative condition. It's not, there are no numbers associated with this. A variable either has variance in the middle or it does not. It has variance in the middle if it satisfies this logical condition. Suction at the ends. The other thing that happens, consider the following martingale. When you are close to 0, let's say, you either become 3/2 of your original value or 1/2 of your original value, each with probability 1/2. There'll be something symmetric in when xt's are large, but ignore that for now. Okay. This is a martingale. It is going to polarize. Eventually, it will go to 0 or 1. But the probability that this martingale will be less than 10 to the minus t in t steps. What is that probability? Well, it's actually 0 because it started off at 1/2, and then after one step, if we were lucky, it became less, became 1/4, 1/8, 1/16. After t steps, it'll be like 2 to the minus t. It's not going to become 10 to the minus t. Okay, so even though this martingale is polarizing, it's not polarizing fast enough, and we really need much faster polarization than that, or it's supposed to get very, very, very close to the origin. This one, on the other hand, will be 10 to the minus t close to the origin after t steps. 100 to the minus t, yes. 200 to the minus t, yes. Anything you want, it is. It's almost like 2 to the minus 2 to the t is the rate of convergence of this martingale. Okay, so this is much faster. This is what we want to have. We capture that by saying, oh, look, in one step, you must show suction at the ends, meaning if you're sufficiently close to the origin, then no matter what constant I specify, the probability that you drop by that constant value is some fixed constant. Theta in our examples is typically 1/2. Okay, so there is some for positive constant, etc., etc. So suction at the end says you must drop by a large value. And what we were able to show is that if you can show these local conditions, then the global condition holds. This is a very neat, simple probabilistic statement. Notice each one of these definitions is just qualitative. There's no a random variable either has strong polarization or it doesn't. There is no it has 10% strong polarization or with probability so much it's polarizing. No, it's either polarizing or strongly polarizing or it's not. It's either locally polarizing or it's not. And our theorem is if it is locally polarizing, it is strongly polarizing. It's not if and only if, but won't you get 2 to the minus t after log t steps? If it has suction at the ends, it will not give you 2 to the minus t after log t steps. It'll give you 2 to the minus t after t steps. It will also give you 10 to the minus t after t steps. Yes, for the last example, we actually get much better polarization. And indeed, in an updated paper, we have a notion of exponential suction at the ends and prove Arikan-Martingale actually has it. But by the way, the Arikan-Martingale does not polarize as fast as that. But it turns out that the two-step martingale, in one step it won't do it, but in 2 steps it actually does do it. And so you get some exponential growth. So some alpha to the t, where alpha is less than 1 after log t steps, but it's not 2 to the minus t. Okay. But yeah, but right. So true, we can get more, but for now, just the following 2 things are good enough. And once you have this, you have strong polarization. Once you have this, you have a thing. So for those of you who care, you can sort of look at these slides offline. And these are, once you decide this is what you want to prove, the nice thing is, there's not a lot of deep math here that you can count on. I mean, I have a martingale, and then I've told you some very broad conditions on how it behaves. I can only use all this in trying to prove a theorem. There's not a lot here. So no very deep, I mean, if you were looking at the specifics of the Arikan-Martingale, the fact that it's a Bernoulli plus 7 Bernoullis, etc., you could imagine getting complicated proofs. We have no Bernoullis, we have no nothing, just arbitrary random variables which have coarse behavioral restrictions. So the proof has to be simple, and indeed the proof turns out to be extremely simple. There's one half of the analysis is done with a simple potential function. The other half is even more sort of simple conceptually. Okay. So anyhow, so once we have this, it works out. The most sophisticated thing that we use is like something called Dub's inequality for martingale, but that's really like a Markov's inequality for martingales, just done right. Okay, so all right. And then once you show all this, what we've reduced our problem to is to say Arikan-Martingale shows these conditions, and that now you actually have to use properties of the entropy and so on, but it's not ridiculously hard properties. If you ignore the fact that we were always looking at conditional entropies and just pretended we were looking at entropies, you get most of the intuition for the behavior. And then when you have to deal with the conditioning, you do deal with the conditioning with a lot of ugly Markov's inequalities and epsilons and deltas, which at the end don't matter because our local polarization condition is so generous that it'll let you do all kinds of tampering. So because of that, this part, is conceptually easy, but, tedious. The rest of it is simple, and you can put these together and you get a very clean analysis. So to summarize, one can show that these, there's very nice tools that we have to show that martingales polarize very strongly. Sorry, this should have been polarized. And this, when you have those kinds of tools, you can actually tell that the polarization matrix will very soon be able to do the compression. In particular, the exact parameters of how this epsilon, tau, and delta behave with respect to each other was crucial to get polynomial gap to capacity, and we do get it. And by the way, I mean, so anytime we get local strong polarization in this definition, that implies that the if we can show Arikan-Martingale polarizes strongly, that implies that you get um, uh, polynomial gap to capacity. That's equivalent statement. And so in particular, this tells us that the polar codes achieve binary symmetric channel capacity at lengths which are very small. Okay, so there's a lot that goes on here. It's, a single talk is too short to be able to understand all this, but I would say, at least you should have a clear outline of what's going on, and maybe if you want to now look at some of the details of the proof, you should be able to find out more about it. And these things are available in our textbook, Guruswami Rudra. So we have a textbook on coding theory available from our website, in draft form available from our website, and it can show you all these analysis in greater details. Okay, so back to the high level thing. What did we do in these 4 lectures? We defined what coding was, what decoding is, and we also talked about list decoding. We told you that you can actually get to capacity with adversarial errors. This is adversarial over large alphabets. Okay, the alphabet size is constant, but still very large. It depends on how close to capacity you want to get. And when the alphabet size is that large, the capacity is just simply 1 minus epsilon. That's a good approximation to what we have. Excuse me. When we decide to go to binary alphabets, we are not able to do as well. We can only correct random errors, but then we are able to do very, very, very well, and we get polynomial in 1 over delta time decoding. I want to stress that there is a big gap between these two. This binary codes versus big alphabet codes. Big alphabet, we are able to do incredible things. For the binary codes, we are only able to deal with random errors, but when we are dealing with random errors, we do so well. And open questions naturally is, combine the two. Let's get polynomial in 1 over delta time codes, binary codes that correct epsilon fraction adversarial errors. Of course, the rate will no longer be 1 minus epsilon minus delta. That's not the right expectation. It should be 1 minus entropy of epsilon minus delta. The query entropy of epsilon is more or less epsilon, but binary entropy of epsilon is much larger. Can you do this? And this is big open question in the field. So open that there are many prior steps that I don't know how to achieve. Okay, so let me tell you about a few of the prior steps that I cannot achieve. So here I'm trying to say, get me for any fraction of errors, get me arbitrarily close to capacity. And by the way, I want it with polynomial in 1 over delta time algorithms. Okay, if I skip this and I said, oh, never mind polynomial in 1 over delta, just get me codes which are polynomial explicit and polynomial time encodable and decodable. Maybe the length n needs to be very, very large compared to the code. I still don't know how to do it. Okay, if I want to get this close to the rate, I don't know how to do it. If I don't know how to get that close to the rate, then let's try some special values of epsilon. Okay, epsilon equal to almost 0 or almost 1. Entropy of epsilon almost 1 are natural choices. We'll try entropy of epsilon almost 1. So entropy of epsilon will be 1 minus something like delta squared if we chose epsilon to be half minus delta. Okay, and if you do this, then what we are really asking is codes whose rate is like omega of delta squared, because 1 minus that's this quantity that we are seeing over here. Yeah, I think I should have done the parameters slightly differently, but anyway, never mind. I made that error, but trust me, what you need if you're looking at entropy, which is that much, to qualitatively achieve capacity is to say we can get codes of rate about delta squared, which are list decodable from this fraction of errors. So even for the special choice of epsilon, I do not know how to do it. Okay, so let's get simpler. Let's skip the requirement that the encoding and decoding are polynomial time. Just want explicit family of codes. If I want to pick a code at random, I know it'll do it. I just want an explicit family of codes. Actually, I don't know how to do that. Okay, so explicit codes is still unknown. Okay, let's go even weaker. Instead of saying it'll correct delta fraction errors with list decoding, let me just say that it'll have distance or half minus delta fraction errors with list decoding. Let's just ask for, let it have distance half minus delta. It's not formally weaker condition, but morally this is a weaker condition. Okay, so I'm almost sure there are results which say if you can do this, if you can get list decodable codes, then you can get codes of this distance with similar rate. But never mind the equivalence. Let's just believe me that this is actually, at least should be conceptually an earlier step. Can you get codes whose distance is half minus delta, whose rate is omega of delta squared? Even this is unknown today. But in a breakthrough work of Tashma, he told us how you can get, that should have been, that's right. Yeah, the rate is arbitrarily close to 2. 2 plus epsilon for every epsilon. I didn't want to put all those quantifiers. I just said 2.0001. Okay, so this is the best we know today. All these levels of unknown have to be jumped over to get to the ultimate theorem that we want here. So there's a long way to go, and this is after having made a lot of progress in the recent years. Okay. So that's all I had to say. Thank you.
Yeah, thank you very much. Thank you very much. Maybe questions?
So on slide 26, you speak about list decoding, not normal decoding.
Yes. Good point. List decoding. Yeah, list decodable codes.
Not just polytime decodable binary codes. In the last open question, it seems that
right. Actually, that list decoding applies to both.
You don't hope probably that you can achieve the volume bound for normal decoding.
Correct. Yeah. So the neat thing about list decoding, and something that I forgot to stress properly earlier, is with adversarial errors, it completely matches what you expect, the capacity kind of behavior that you expect from random errors. With unique decoding, you don't get that. Unique decoding, the maximum fraction of errors you can correct under unique decoding is roughly 1/4. You never go beyond 1/2. You never get close to 1/2. Right. So this is why I think we should really just shift focus to list decoding, because that's really a good way to capture and strengthen random errors.
And if you have this open question resolved positively, then you can, from that, you can get decoding random errors by just adding as a hash to list decoding.
That's right. You could do that exactly. And actually, it may be even easier in the sense that you will get a bunch of things, but it's very unlikely that you will, the probability that some other code word will actually map to inside the ball will be very low. So you can easily, just by saying, oh, I'll give another epsilon, another delta away, or instead of epsilon, using epsilon minus delta or something like that, suddenly say, oh, most of the other options went away and only the real code word got left.
And sorry, if one more question. So for your, you have the same in this butterfly thing. You have the same construction for independent of P. So
Right,
is it some kind of understanding? For example, imagine that you increase the P. Then the serious bits on the right hand side change. We get more and more. For example, do we just add the new, or they are rearranged? Or if we just take a permutation of the construction on the right-hand side and consider the bits in different order, they still have this nice property that every one is either determined by the previous one or independent of them. Or
right. So
kind of miracle.
I think,
what else happens?
Yeah, I mean, so it does grow monotone. So if I have a certain set of bits which should have been output because I have P set to a low value and now increase P, I will take a superset, which is partly answering your question. That being said, it is possible that with some other, if you had gone through these bits in a different order, then you might have come up with a different subset of these bits which would have had the same property. So it's not, I mean, it is conceivable that this collection of bits collectively have exactly the same information condition on the things above as those other collection of bits. So
of course we have different bits, but if we have A, B and A plus B, A XOR B, then of course it can be, but still for every permutation, you still have the property of this dependence or non-dependence.
Right. Once you fix the permutation, you have the, you have this monotonicity. Exactly. Once it becomes entropic, for larger and larger values of P, it will be more and more entropic.
Strange.
Yeah. Andre asked on the chat, if you do an encoding with a random matrix instead of iterating the Z operation, do we have polarization? Great question, Andre. Indeed, a random matrix would give us the polarization. It will be invertible with reasonable probability, and then it'll be polarizing with very high probability. However, you don't have the Z operation was useful in getting the decoding, which you will not get for the random. So to get efficient decoding, you need some more structure, and that's where the Hurricane structure is just great.
Still, I'm sorry, that's so strange. So for every output, actually you have a XOR of some subset in the input. So you have some family of subsets of n subsets of an element set, which have a strange property that if you take any even different Bernoulli variables, they have this property. Does this, so in terms of families of subset, does it have some combinatorial meaning, and we can just construct something with combinatorial properties and with this butterfly, or it's just that what is happening?
So yeah, determining the structure of the sets which have enough entropy, which subset of these will have entropy condition on the previous things. It really is. We are very far from understanding it. One hope initially was if you took all the large subsets, they are entropic, and if you take all the small ones, you can throw them out. And this would have basically told us that actually Reed-Muller codes achieve capacity. We haven't been able to prove that. We have various analysis which says that when you do this, you're almost there, but not quite.
But if you take two large sets which are close to each other, then they are not. If the XOR is small, it's not good.
Right. So in this case, actually, the sets do come with a lot of structure. That these are subsets which, either they're, if you have a large set and a small set, the large set will either completely contain the small set, or it will be disjoint, etc. So those kinds of properties, but yeah, for these particular class of subsets, it turns out that you could just take all the big sets and then the next bigger sets and the next bigger sets and so on. And that's a pretty good process, but towards the end, it sort of starts to fail, and then you have to do some perturbation. And so at the end, you're not getting a very clean picture, but towards the end is where you're making most of your important decisions anyway.
Thanks.
Sure thing.
So let me stop the recording.